Testing. Okay, now the microphone is on. Sorry about those who are just joining us. You've got your quiz. All right, if you're done with the quiz, feel free to pass it over. It shouldn't take too long. So if you're ruminating too long on this, it means that you don't know what's going on, I guess. Yeah, so you're basically just going to identify the P and then just say whether it converges or diverges. That's it. So don't write too much on this particular quiz. Okay, so some of you, of course, front. I know, back row. I'm going to give you a little bit more time. Don't worry. Very nice. Yeah, just going to throw it. We could try. See if I can catch it. I don't know. Let me see. You have to develop those skills. Thank you. All right. And I don't want to rush you guys, the back row, because you were the last to get it. So I'll wait. I'm not rushing you either, am I? Wait, I have extra quizzes? Oh, there was an extra one. Oh, Ryan. Usually I print just the right number. Thank you. You're all set. I'm not rushing you, am I? Okay. Yeah, I'll come back for you guys. Don't worry. Now you're all set? You're happy now? Back row? Good. I always like it when you're happy. Yeah, what's that?
I hope so.
Yeah, good. Yeah, yesterday was a little rough. I graded it. I just didn't bring it with me. I think I was just depressed. I forgot to grab it. But yeah. Is this mine? No, that's yours. Or is it mine? No? Oh, that's right. That's yours. All right, you're ruminating still. Take your time, but try to hurry up. Oh, here, let me come around. Thank you. All right, excellent. Beautiful. All right. You have answers for all of them? You have answers. You just don't like your answers?
I'm not sure.
You're not sure, but you're going to find out in just a minute. Okay, well, we'll find out. All right, do I have all the quizzes? The P-series quiz. Okay, so just to remind you, don't worry, I'll get this figured out here. Where did it go? Oh, here it is. Let me just do this. There it is. So the P-series, just to remind you once again, is that if the P, that's the power, if the power is bigger than 1, you converge. If the power is less than 1, you diverge. So that's all you have to do with the P-series test to see if it's convergent. Wait just a minute. Let me make sure that I can find this again. There we go. Yeah, there's my thing. Okay, just wanted to make it easy to find on my list. And so let's go ahead and see what these powers are. And so this, I'm going to rewrite this. You didn't have to do this. Make it big for you. So this is 2 over into the 1/2 power. And so the power here is 1/2, which is less than or equal to 1, which means you diverge. So that's the power. It's the power of n in the denominator. So this one here, this power clearly is 2. P is equal to 2. And so that is bigger than 1. And so that converges. What does it converge to? It converges to pi squared over 6, but you don't have to memorize that. That's it's difficult to show that sort of thing. But then this last one, that one took a little bit more work, but not too much. You just had to rewrite this like this, into the pi minus e. So the power here is pi minus e. Pi is 3.14159. E is 2.71828, and so pi minus e is definitely less than or equal to 1, so that will diverge. So that's it. There's your thing. And so it's important to keep these. This is supposed to be the easy questions. It's important to keep those straight because they're going to be sort of the cornerstone for the tests that we do today and actually moving forward. Okay, before we move on, let me just mention, I don't know how I missed this, but when we were introducing series it's in section 11.2. So the very first section about adding things up, there's this theorem, it's number 6, it's on page 713, and it's called the what do they call it? The test for divergence. I've heard it referred to in a couple of different ways. It's a pretty basic idea, and that is if you're adding together a bunch of numbers like this, 1/4, 1/8, 1/16, and so on, the only way you have any hope of these converging, that is adding up to something, is if the individual terms get smaller. Kind of makes sense, right? And so the way that the rule is, and we're just going to mention this briefly because it's pretty obvious, is that if the terms don't converge to zero, then the series will for sure diverge. The series diverges. Now, the converse of this is not true, nor is the inverse of this. So just be aware that this only goes one way. If the terms don't converge to zero, then the series diverges. If the terms do go to zero, you don't know anything. Well, you know that they go to zero, but you don't know because, for example, this 1 plus 1/2 plus 1/3 plus the harmonic series, or a p series with p equals 1, this actually diverges, even though the terms are getting smaller. So the main thing is that if you have something like this, let me think of one that would, let's see, be easy to illustrate. How about if we do this, plus 2/3 plus, how about 3 fourths, I don't know. Yeah, I guess this works. It doesn't really matter. 4/5. I didn't start correctly. I should have started with 1/2, but whatever. Plus 5/6. You see what's happening here is that these terms are actually getting bigger and they're getting closer to 1. And so if you're adding up those terms, you're never going to converge because the sum will get bigger and bigger forever. So this for sure diverges. Okay, so that's the idea. Let me go back to my little, here it is, there it is, the series flow chart, and we're going to add to this today. We've got some PowerPoint, don't worry. So just to remind you though, here's where we are. We want to know, the whole point is, does a particular series, does it converge? So the first thing to do is to ask yourself, is this one of the easy ones? And I don't care what order this goes in. Actually, the first 3 things that you do, probably the very first thing you do is to, I don't know. Actually, the way I do this is I ask, is it one of the easy ones? Is it geometric? If it's geometric, it's easy. If this is a P series, like the quiz, then it's easy. So that's what these are for, is it geometric? Yes or no. If it is P series, yes or no, then you've got an easy job. If it's not one of your favorite ones, P series, geometric, then you have to ask other questions. So this is going to be a big, long list of questions. So just strap in. So the first, though, this is another easy thing to check. Is the limit as n approaches infinity, this is the test for divergence, is the limit equal to 0? And if it is not, then for sure you diverge. I have this example over here if you need one. This example is a divergent series because this term, the limit as n approaches infinity, is not 0. It has to be 0 for this thing to converge. So that's another thing that's relatively easy to check. So then the next thing you do is, well, if this is 0, then what do we do? So here's the example. Well, here, let's see. I want to erase some of this because this is all extra stuff over here. Okay, let's delete. Good, gone. Delete that too. Okay, so you might say, well, what sort of series would we be looking at if we got down to the bottom? Well, there are a lot of series, but here's one example. If you have something like this, the sum where n goes from 1 to infinity of, say, 1 over n squared plus 1. Now, I realize that we have the integral test for this. Oh, we should throw that on the list. Because the integral test works for this. In fact, it was on your quiz. And I'm still surprised that some of you don't know that the integral of 1 over x squared, or 1 plus x squared, whatever it is arctan. Yeah, so remember this. It's my favorite series, or no, my favorite, it's also my favorite, one of my favorite series, but it is one of my favorite integrals. So make sure you know this. It's going to be everywhere. I always slip it on. I stick it wherever I can. But anyway, getting back to this. So what do I do with this? Well, I suppose I should erase this. Let's go ahead and add the integral test to our, I'm going to erase that and say, let's do the integral test. Okay, so the next one, and then we'll get to the comparison test. So don't worry, we'll be there in a minute with the comparison test. So the next question that you're going to ask yourself is, does A sub n, is it a decrease and positive? Okay, maybe that's a bad word here. Let's do is. Is that decreasing and positive? So if it is, then you can use the integral test. Whoops, what is this? Okay, so I'll just put a little box here. I don't know what the right thing to do is because I'm not really a professional flowchart maker. But if it is, then you're going to use the integral test. Maybe. I'll just put a question mark there because you might find that the integral test isn't worth it with some sequences or series, because the integral that you'd have to do would be too hard and you'd say, I'm going to skip that and go to the next one. That's fine. These are options, really. So do you want to do the integral test? You can if you want to. If this series does not decrease, or the sequence is not a decreasing positive sequence, then you can't do the integral test. And there are lots of sequences that are not decreasing and positive. Here's a good example. Anytime you have -1 in there, then this thing does not decrease. So this times 4 over 2n minus 1. So this is not a decreasing positive sequence. 1 to infinity. Yeah, I think I want to do a plus and go from 0, but whatever. So that doesn't decrease. It jumps back and forth. It's sometimes positive, sometimes negative. So you can't use the integral test. So then you have to ask, well, what's the next thing that you're going to do? Well, that is the comparison tests. So we'll put that here. Compare. So I'll make that a question mark so that, and then we'll do the next thing next time. Okay, so what do I mean by compare? Well, there's two options for comparisons. Let me move this out of the way. We'll use this eventually. Let's shove it down there. So there's two options. There is the direct comparison, and there is a limit comparison. Limit does not have a P in it. Limit comparison. So those are the two options. So I'll just leave that as a little box because it's self-explanatory once you understand those two sequences. So here we are. I know it looks really crazy, and it's actually going to keep going. So if you've written this on it, whoa, I don't know what that stuff is. But anyway, if you've written it on a piece of paper, it's probably going to go on to yet another page because there are more tests to sort out. But hopefully after a while, you'll get used to the way to think about these. And there are a couple of go-to like tests, like down here, when we get down below this, there's some that I always use first, even if, yeah, they're easiest to deal with. But we need to do the comparison test first. So let's switch over to PowerPoint just briefly. Where is my PowerPoint? It's right there. This is annoying me because I keep getting notifications. Someone is texting me multiple times. Okay, so the comparison tests. What this is referring to is if you have a series that looks similar to a series that you are familiar with. Let me use n cubed plus 1 instead of n squared plus 1, just so that, so that it's obvious that it's definitely not the arctangent. So this one, it looks like this. So those look like one another. They share some sort of a common root. So what I want to know is, first of all, the one on the right, does that one converge? Since it looks familiar, you should know, does it converge or does it diverge? So take a minute and think in your mind, does that one converge or diverge? And I'll pick a random person. Darren knows. Darren, does this thing converge or does it diverge, the one over on the right? It converges, you said? And why does it converge? It's because it's a p series where p is equal to 3, which is greater than 1. So this is a p series. So those look alike. And so maybe, oh, so this thing converges. So maybe we could say that this one, because it looks so much like that, you would think maybe it converges as well. And in fact, it does. It's as if this one shares some of its reflected glory with that one. That there's a comparison there. So we'll see exactly why it converges in just a minute. But let's do another one just to see if you get the picture here. Let's say I had this series. Let's see if I can do this right. How about if I do this? N over, oh, no, we'll do it this way. I don't want N. I should have thought this through beforehand, the introductory series. Okay, so how about this? N goes from 1 to infinity of N times pi over E. We'll pick those again to the N power. Let's do that one. Okay, so that one looks sort of like, so looks like this one. I mean, because the thing that really is dominating this over here, I mean, there's an in there, but what's the big deal about an in? This thing, though, that I'm familiar with, that is geometric, right? This is a geometric series. It's something raised to the n power. And so Americo knows about whether this converges or diverges. What do you think, Americo? Does that converge or diverge? It does diverge. And do you know why it diverges? Yes, okay, I like that. Smaller on the bottom. I would have done it this way, but it's totally fine. This one diverges. The reason why it diverges is because the common ratio, pi over e, is bigger than 1. And this is horribly confusing, is it not? That p series, you want the p to be bigger than 1. With geometric series, you want the r to be less than 1, or rather the absolute value of r to be less than 1. So anyway, these look alike. So this one diverges. And so perhaps the sins of this particular series can be found over here. And that's the question we want to know. Does this diverge as well? And indeed it does. And we'll explain why when we compare the two. So you're always going to be on the lookout for a series that looks similar to another one that you're familiar with. So notice that I'm comparing with the P series and the geometric series. Those are the two biggies that you really need to have solidly. In fact, I'll just say right now, I'll commit myself that tomorrow I will have a P series and a geometric series at the top of the quiz, where you just have to say, does this converge or diverge? Does this converge or diverge? Tell me why. Okay, so we'll get to that tomorrow though, but for now, let's take a look at this. Does this remind us of another similar series? I'll bet it does. Tell me what this reminds you of, and we'll pick a person in just a minute. So try to think of what does that look like? Is it geometric? Is it a P series? All right, Christopher, what do you think what does that remind you of? Yeah, 1 over 2 to the n, very nice. So it looks like that series, and that's geometric, that converges. And so does this one converge as well? Well, let's see. So yeah, they're geometric, whatever. Why do I have that? I don't know. Yeah, so that's whatever. Anyway, That's not really that important. But here's the deal. This is the comparison that we're going to make. That is a true statement, is it not? That if I take 1 over 2 to the n and I throw an extra 1 in the denominator, it makes the denominator bigger, which makes the whole fraction smaller. And so that is the comparison that we need to make. And since that is true, then let me just see, does this actually build? No, I don't like what's there, so I'll just write. So what that means is that when I add together a bunch of these, that will be less than when I add together a commensurate number of these. So if I go n equals 1 to infinity, n equals 1 to infinity, that's true. So if this is true, then this will be true. So if this one converges, then this is smaller than this, and it will also converge. Now, there are a few caveats that we have to make before we actually use this for real. And so let's see, let's formalize this. So here's the deal. This only works when the series terms are positive. We'll get to negative terms in a bit. I showed you that example that the -1 to the n thing. We'll do that, I don't know, maybe next week. But for now, or maybe Friday, I think it is. For now, we're sticking with comparisons. So this is what's called a direct comparison test. And so the comparison is that if your series is smaller than a convergent series, then your series will also converge. And then the opposite is kind of true as well, is that if your series, or I guess it's the contrapositive technically, that if your series is divergent, or no, if your series is bigger than a divergent series, then your series will also diverge. So there's the two comparisons. We're going to practice this. In fact, let's back up to the two that we did at the very front end and see if we can apply this. It's not that hard, and it's pretty easy to see why, that if you make numbers that are bigger than something that adds up to infinity, then you're going to go to infinity as well. Okay, so let's see. Why is this not moving? There it is. Let's go back to this. So let's go back to this thing here. Now, you told me, or someone told me, that this series up here converges. Converge, okay, I can't really spell because it's so little, but that one converges, and 1 over n cubed plus 1 is actually smaller than 1 over n cubed. That's a true statement. And so this is smaller than a convergent series. Oh, I should also point out there are no negative numbers here, right? Anytime you throw a negative in, you can't use this test. So I just want to warn you about that. So, but anyway, less than a convergent series. And so this one also converges. Also converges. So it's important that the comparison is the correct direction. This is less than something that converges. So now this one diverges. And if you look at the terms and compare them, it turns out that n times pi over e to the n power is actually bigger than pi over e to the n power, as long as n is bigger than 1. Now, when n equals 1, then they're equal. But I guess if you really want me to, I could do that. But as long as n is bigger than 1, this will be bigger, this is bigger than this. So you're adding together numbers that are bigger than these numbers, and these numbers diverge. So that one will diverge as well. This one also diverges. Diverge. Okay, if I can only write. Okay, so we need some examples, don't we? So let's try. Oh, yeah, that one works. So determine whether this series converges or diverges. And I'm pretty sure that you can guess without even doing the work, but we need to do a little bit of like proof-like stuff. We don't do a lot of proofs here. In fact, no one does these days in calculus. But we do need to explain ourselves. So If you think it converges, tell me why. If you think it diverges, tell me why. Take a minute, work with your friend, figure out what you're going to compare this to. Let's see why my phone's blowing up here. Okay, great. Good. Okay, let's see how we're doing. Ethan, what does this series up here remind you of? What would you like to compare that to? I love it that you're going to throw the 5 in there. That's beautiful. 5 over n squared. Okay. Yeah, I mean, that's perfect. So a lot of people forget the 5 and think it doesn't matter. It does matter. Well, it will eventually. Thank you. Okay, so 5 over n squared. So let's see. What kind of series is that? Ben Peoples. Ben, what kind of series is that? It's a P series. Does it converge or diverge? That's right. Yeah, so this is super important that you got this P series and then it converges. Why does it converge? Because P equals 2, that's greater than 1. Excellent. You're going to get sick of hearing this every time. Okay, very good. So now I need to do this. I need to know, is this what I'd love it to be? Is I'd love this to be bigger than this here. Is it bigger than that? Maybe what I should do is start with what I have there. 2n squared plus 4n plus 3. And I'd like a series of inequalities that end with this. So can you get me on this path to get from that to this? Can you fill in the connections? It's kind of like one of those puzzles where you have a word at the top, like a word ladder, and you're supposed to make changes until you get to the bottom. And anyway, let's see what we have. Michael G. Michael, what do you think? How can we get from here to here, or do you want to just go straight over there and explain why it is that smaller than this? There you go. Yeah, I'm going to do an extra step, though. I trust you on your particular analysis, but I'm just going to do 2 steps instead of 1. What he said is perfect. If you add anything to the denominator, not subtract, by the way, this doesn't work with subtraction, but if you add stuff to the denominator, it makes the whole fraction smaller. So if I get rid of the stuff that I have added to the denominator, it actually makes the whole fraction bigger. So yeah, I left the 2 in there just as to emphasize the idea. And then, I guess I won't insult anyone's intelligence by asking why the next inequality is true. Because it's obvious. This is 2 times n squared. This is just n squared. This denominator is bigger than this one. I'm good. So that is smaller than this. Therefore, this converges. So to show that something converges using the comparison test, you have to show me what you're comparing to. You have to explain why that thing converges or diverges. And you have to show me why it is that this thing is smaller than that thing. So there's a bunch of stuff that goes into this, a lot of work. Okay, so that's great. You did great. Let's try another one. How about this? Oh, there's 2 of them there. 2 of them. The top one is the hard one, so we'll do that one. We won't worry about the bottom one we've done already, I think. Yeah, we did. So we'll do the top one. So see if you can figure out why, if that thing, does that converge or does it diverge? Take a minute, figure it out. And of course, the first thing to do is to figure out what you are comparing to. So I'll get myself set up here. All right, Ben H., you're up. What would you like to compare this to? Well, here's the trick. When you don't know, what you do is you look at this and you say, how can I make it easier? What's the problem? What do you hate? Oh, I hate it as well. Let's get rid of, what if you got rid of that natural log? What would you have? Over K? Yeah, 1 over K. Well done. Okay, so make it simpler, and then maybe this will work out. I'm not guaranteeing that it'll work out, but this is a good go. So you take it, you make it simpler. It's kind of like what we did with the last one. We made it a little easier. We got rid of all the junk that was in the denominator. Okay, so now let's ask the question, does that new series converge or diverge? You're not here, but you would probably know. Let's see if I can find another volunteer. Thomas, what about this series? Does this converge or diverge, this new one? It diverges, you say? Yeah, because this is, what kind of series is that? Yeah, a P series, power series, P series. And the P here is equal to 1, which is less than or equal to 1. The rule is if the power is less than or equal to 1, you diverge. Diverge! Now I need to know what is the comparison between this and this. So what symbol do I put between those two? Oh, you're not here either, but you would probably know. Oh, well, Karen knows. Karen, is this thing bigger or smaller than this thing? It's bigger, yeah, because you have something in the numerator that is bigger than 1. Well, it's bigger than 1 as long as K is bigger than E. So I suppose I could qualify this and say, as long as K is 3 or more, this will be bigger. So that's the case for almost all values of K. I suppose just if we want to be really correct, I'd say when K is greater than 3. But honestly, if this was an exam and you just wrote this down, I would be like, yeah, you know what's going on. I'm not super picky. I probably should be more picky, but I'm not. But that's to be complete. So since I have a series that is bigger than something that diverges, it means that the actual series also diverges. I know, so much to do with these. Let's see, how much time we got? 9:47, good. Okay, let's do this one. Here we are. Okay, so this one's a little tricky because of a couple of things. But go ahead and figure out, what are you going to compare this to? Okay, so Christian, what would you like to compare this to that you're familiar with? Yeah, it's that extra 1 is the, the extra 1 is the thing that is a problem. So compare it to the sum of 1 over 6 to the n. Very nice. Okay, now we need to know, does that thing converge or does it diverge? Fred, what about this series over here? What kind of series is that? It's not a power series. What's the other one that you're familiar with? It is geometric. Very good. It is a geometric series. Do you know what R is for this? I'll rewrite it and then you'll know. Here, just a minute. I'm not letting you off the hook yet, Red. What if I wrote it like this? Would that be more familiar? Yeah, so what's R? 1/6. Very good. Okay, so R is 1/6. This thing converges. Very nice. So if I could somehow say that what I have here is smaller, that's the key. If it's smaller than the 1 over 16, then I'm in good shape. But there's a problem, isn't there? Well, there's actually quite a few problems with this. Problem number one is I probably should have written this as starting at 2. Because when n equals 1, I have 1 over 0. Like plug 1 into this. So let's correct that right off the bat here. Let's make this go from 2, and then we'll change this to 2. This thing still converges over here. So that's the first problem that I just happened to notice, that I was typing too quickly, and I'm like, yeah, throw it in there, it'll be fun. But no, not that fun if it doesn't converge. But anyway, so there's the first problem. The second problem, 1 over 6 to the n and 1 over 6 to the n minus 1. What is the comparison? Is this, which one is bigger? That's the question. Which one of these two is larger? Michael H., do you know which of these two is larger? The one on the right. Really? Oh, that's too bad. Because notice what we have here is we have something that converges, and then this thing is bigger than something converges. Well, you know what's bigger than something that converges? Infinity. So we don't know if this converges or not. So just because we have something that looks convincing, it's not good yet. So it turns out that this is much more difficult. Now I'll show you the comparison that you can use. However, if I were doing this one, I would actually pivot and I would use the second comparison test. So with this one, it's a little harder, so I would use the other comparison test, which we're going to go over momentarily. But first, I wanted to show you that it is possible to do this using the direct comparison. So here's what I'm going to compare this to. The sum where n goes from 2 to infinity of 1 over 3 to the n. So it turns out that this is actually smaller than this. How do I know? Let me show you. But this is tricky. So this, I would expect that if you had this on your homework or on an exam or a quiz, that you wouldn't use a direct comparison, but rather you would use what's called the limit comparison. But let me just go ahead and show you why. If you're curious, how do you know? Here, I'll show you. So this is, let's see, 1 over 6 to the n minus 1 is the same as 1. Oh, no, it's not the same. Wait, what is this? Sorry, I got all excited. What am I doing here? I want to put a 2 to the n here. Just a minute. What is the deal here? Minus 2 to the n. If I make the denominator smaller, the whole fraction is bigger. Okay, yeah, I'm good. Sorry, I got confused for a sec for some reason. It's not equal. There. Is this true? Let me think for a minute. So I'm making the denominator smaller by putting a bigger number here. So this is going to be bigger now. And then, yeah, like I said, it's tricky. And then I can write this like this. Oh, I blew it. Sorry. I wanted to put a 3 to the n here. Try again. 3 to the n. Okay, that's better. Okay, so this is equal to 1 over 3 to the n times 2 to the n minus 3 to the n. Still true. Whoops. Oh no, why did that switch? There it is. Okay, so now that thing is equal to 1 over 3 to the n times 2 to the n minus 1. And then finally, all of that is less than 1 over 3 to the n. So I know, how convoluted is this? I have to invent a 3 to the n. Inequalities are hard, at least coming up with them. So I would encourage you that if you had this problem, rather than doing a direct comparison, which involves all kinds of convoluted thinking, or not convoluted thinking, just having to do all this extra algebra, let's do the other test. The other test. So what is this other test that we're interested in? Well, the other test is called a limit comparison test. In a limit comparison test, it allows you to compare something like this to something like this without having to link the two via an inequality. So you don't need to know which one is bigger or smaller. So when we look at the comparison tests, here's the way that I think of them. is if it is obvious, like it is back here, I think, if it is obvious that you're going to compare this to this and there's an obvious connection, then use the direct comparison. But otherwise, if it's not immediately obvious, here's another one up here. These two were both obvious. They're easy. If it's not immediately obvious, then you're going to use what's called the limit comparison test. And so here's an example of a limit comparison test. This is geometric. This converges. This is related to this. However, it's not entirely clear which, well, it is clear. This is actually bigger than this. So this converges. That's bigger. Does it converge? Well, let's find out. We're going to use what's called the limit comparison test. The limit comparison test, I know it looks scarier. However, it's super useful. So we're going to do a limit as n approaches infinity of a ratio. And I don't care. I don't care which one goes on top. You pick. I don't care. Pick whichever one's more convenient, whichever one you feel better about. Put whichever one on top you'd like. But the important thing is that when you do this limit, so if you want to write down anything, do this, write this down. That, if that is true, then that will marry, or it will like a wedding. It's like a wedding ceremony. It will give both of those the same fate. So in other words, those two will be linked in holy matrimony, but they'll be linked somehow. And if this one converges, then that one will. If this one diverges, then that one will. It makes them share the same fate. So if you can find a limit, if you can find another series that has this a limit, comparison, then these two, those two, they share the same fate. Share the same fate. That's the key. There's some qualifications here, is that limit has to be non-zero and finite, but it's pretty straightforward. So let's take a look at the limit for these two. I don't care which one goes on top. Here, I'll zoom out in just a minute, but I need some room to make my limit. So let's do this. We're going to do the limit as n approaches infinity of, let's just put this 1 over 2 to the n, that's that one, over 1 over 2 to the n minus 1. So just to be clear, I'm taking the one on the right and sticking it in the numerator. The one on the left is in the denominator. So I don't know if you can see that. Okay, so let's do this limit, and we'll see if these two series are married. And if they are, then they get to share the same fate. Okay, a little bit of work here. Oh, this should be an n, shouldn't it? Sorry, that should be an n. Okay, so the PowerPoint has limitations. Okay, so we've got this will equal, if you'll forgive me for skipping, well, just combining maybe 2 steps, not too many. I have 2 to the n minus 1 over 2 to the n. So I'll explain though. Here are the steps. First thing is that 1/2 to the n is the same as 1 over 2 to the n. And then I divided fractions, and you know how to divide fractions. You take the one on the bottom and flip it and multiply. So that's why this stuff ended up in the numerator, and the 2 to the n up there ends up in the denominator. So far, so good? It's not a difficult limit, really isn't. Okay, next. This is going to equal the limit. I'll be careful here. I won't skip any more steps, I promise. Now, I'm going to write this as 2 fractions. 2 to the n over 2 to the n is 1, minus 1 over 2 to the n. 1 over 2 to the n. All right, now I'm pretty confident that you can take over for me. So let's find someone. Lewis wants to tell us about this. Lewis, what is the limit as n approaches infinity of this thing right here? Yeah, so that's 0. So I'm going to do 1 minus 0. So that's easy. So this is just going to be 1. 1. All right, now let's back out again and see what this theorem says. So this limit comparison test says that as long as you when you do this, you get a number that's non-zero, so it can't diverge and it can't be zero. As long as you get a number, then these two share the same fate. So if this one converges, that one will, and vice versa. If they diverge, then they will. So these are linked now. Put a big box around them. They are linked. And since the one on the right converges, this one will converge. Converge. And so there are ways in which this is way simpler than this over here. You see all that? This is confusing. I guarantee that some of you have no idea what's going on down here. But you could all make a limit. Let me show you the limit for this one. Here, I'll put this up for just a minute more. Then we'll back off and do that one with the 6 to the n. So let's do the limit for this one. So we'll use the original. I'll just box off a little space down here for my limit. So here's the limit. We're going to do the limit as n approaches infinity. Pick one of them to go on top. It really doesn't matter. I mean, it matters a little bit, but not too much. So you can see I've taken those two series up there, and I took the one on the left and divided by the one on the right. Now this is almost the same limit that we just did, so I'm not going to spend too much time on it, but just show you that this is, I think this is so much easier for this particular problem. So that's going to equal limit as n approaches infinity of 1 minus 1 over 6 to the n, and that equals 1. And so they'll share the same fate. And in this case, their fate is that they both converge. So for me, here, let's just draw a dividing line there. The stuff on the left is far easier to understand than the stuff on the right. Now, sometimes doing a direct comparison it's fine, but sometimes not so fine. And so doing a limit doesn't look that bad when you compare it to doing that. Okay, so what do we got here? Convergence, divergence. Just find a nice one here. How about this one? That one's fun. So let's test this series. And I want to use a limit comparison because I don't know how to navigate all of those n's. So let's go ahead and do a limit comparison. So first off, we need to pick a series that we're going to compare that to. So why don't you take a guess, but I have some guidance, don't worry. I'm not going to leave you hanging. There's a couple of hints that I can give you to help you figure out what you're going to compare. There. So what I would suggest you do as you try to figure out what you're going to use to compare is look at the numerator, take the biggest thing in the numerator, and then do the denominator and do the same thing. What's the biggest thing? Like, what's the big hulking, like dominant alpha dog or whatever? Like, what's biggest in these? So let's go ahead and we'll separate out those. So let's pick a couple of people. Hayden, what's the biggest thing in the numerator here? Yeah, n is the biggest, as long as n is bigger than 1, right? Like, because n, you're talking a sum where n goes from 1 to infinity. So once you get beyond 1, and certainly when you get to 10, 10 is bigger than 1, 20 is bigger than 1, million is bigger than 1. So yeah, you have to think sort of long term with this. Carson, what about the denominator? What's the biggest thing down there? Yeah, into the 7th, same reason. As long as you're bigger than 1, into the 7th is huge. Like you think of 10 to the 7th? What is that? It's 10 million compared to 10. I'd rather have $10 million than $10. So take the biggest thing in the numerator, divide it by the biggest thing in the denominator. That's usually what you want to use for your comparison. So let's see, what does that equal? That is the same as this. And so the question is, does that converge or die? Well, there's actually two questions. The first one is, can we make this comparison? And then the second one is, do they converge or diverge? Yeah, I'm looking at the clock. I realize there's not a lot of time. So we're going to pause here because I actually split this homework. I got to show you something though, so don't pack up quite yet. Um, the yeah, I broke this particular assignment into two. Let me see, where is my Calc 2 stuff? Here it is. Give me a sec. I can't see a thing without my glasses if I'm close. And then when I look at the screen, I have to take them down. It's terrible. Okay, just a minute. I have a mirror here. Okay, so let's see. That's tests. Yeah, I've already put the practice test. Did I? Yeah, practice test. Oh, that was from 5 years ago. Hence the the name of my solutions. We'll talk about that next week. But where is my homework zone? So I've, like I mentioned, I've added homework all the way through the end of the semester, but the dates are not quite correct. Especially when you get down here, you'll see that the dates are 5 years old. So ignore the dates down there at the end, but right up here, where is it? 22, 21. There it is, 22. Homework 22 is A. So I've split this into two pieces. So remember, you're going to show me the series you're using for comparison. I've decided to just put my problems here because that's what I did in the olden days. So that's due tomorrow. And then the other half, if you want to get started on it, these are all, I believe, direct comparisons for tomorrow. And then Friday is the limit comparison stuff. So we're taking our time, and you can see we've stretched out 11.5 to a couple of days. So we're going to, and eventually, apparently 5 years ago, I started having answers. That's why I decided I'll just do the same homework that I did 5 years ago, because I can just, use the answers and so on. So when you look at that homework, it's a little lengthy. Maybe I'll put some lines in for the weeks because it is kind of hard to navigate. So I'll try to make it look better, but for now, that's the deal. And I do have the test for next week, at least the prep.